Welcome to this video. My name is Mark Scythian, and in this video lecture we are going to cover applied quantum mechanics. And so essentially we're finding the relationship between matter and energy. So if we were to take an example of a laser beam, we could solve for the matter component through quantum entanglement of the coherent waves within a laser. So, of course, the acronym LASER stands for light amplification by stimulated emission of radiation. We have such characteristics as refraction, entanglement, etc. So if we have a set of coherent waves that entangle with each other, we then have the particulate equilibrium state or the ground state, the neutron ground state. So we're able to then have a complementary particle or chemical to the non-physical energy. And so we could describe that by the Einstein-Rosen bridge, E is equal to mc squared. So if we were curiously solving for the matter or material component of a purely energetic field like a laser beam or a light source in general, it would be the ratio of the given energy of the magnetism or light or laser divided into the speed of light squared. So this is known as the Einstein-Rosen bridge as a function of special relativity. And we must focus on the four states of matter: gases, liquids, and solids, of course, most know about. But the fourth state of matter is the plasma matter. This is the ground state, electron or neutron state of proton, electron, input, output, etc. So there is an entanglement of the cycles or frequency of the input-output functions of the electron and proton. And so we reach this trend or neutral or ground state for which the conversion of energy into matter occurs. So if we were bringing a state of matter, some material or some particle, if we moved its speed to the speed of light, it would no longer be a material object. It would actually reverse its entanglement and become a frequency of energetic light and or an electrophotonic state in the form of magnetism or light or electricity even. So we have issues with the entanglement and the frequency phase shift between all of these different energetic patterns, and the correlation between matter and energy is then described, but then we move into informatics. So the data stream or the conscious or quantum information is then inducing the energy, which is then inducing the material. So of course Newton described material and Einstein described energy. We'd say Einstein, Planck, Tesla, Rutherford, etc. And so we're in the post-quantum era, where by inducing informatics, we can then induce quantum response and then induce the material outcome. So of course we have things like the internet, we have quantum superpositioning, we have the 3D printing apparatuses, programmable matter, basically, and the R&D state. So all of these are a function of quantum mechanics. And so if we were just curious, 1,000-watt laser, what would be the material or the mass component of the laser, even though it is purely energetic? There's no mass to a laser. So we find the correlation of energy to matter through quantum entanglement. So that is the function of the energy. In this case, joules, energy divided into the speed of light squared, that speed of light in meters per second. So 1 watt of power is also equal to 1 joule per second. Okay, so if we scale it down and enter a 1,000 joule per second function over the speed of light squared, which is what we have here in the multiplier tree, so then we have the 1,000 joules per second divided into 9 times 10 to the 16 power meters squared. seconds squared. So through factor label cancellation, we can then isolate the kilograms matter within the 1,000-watt laser beam. And so that's 1.11 times 10 to the negative 14th kilograms of matter at the c-squared function, a scaling factor again. So we don't want to do things like reduce it down with a square root again, because it is a function of c-squared as the scaling factor. So then from that point on, the practicality comes out by applying that calculation to the kinetic energy equation, 1/2 mass times velocity squared. And so upon doing so, we can isolate the velocity as is as the speed of light. And so this practically comes down to the ability to transfer 495 joules per second, or 495 watts of heat through the laser to the endpoint or the target. So there's other things you can do with that laser, including piggybacking microwaves onto them. So now you have a maser microwave amplification by stimulated emission of radiation. And so then things become very practical to actually physically change the environment. For example, laser conflagration mining. If you used, let's say, 100,000 watts of laser carrier medium with, at least 10% of that in a microwave power add-on, you could definitely do things like pulverize or liquefy the rock and make your own reinforced structure. So these concepts have been around for 40, 50 years now, but when you hear the word quantum, all it means is the subatomic state. So you're doing a lot of quantum calculations in chemistry with quantum numbers. The practicality out of the chemistry is the physical chemistry, which is a major subject in mechanical engineering, electrical engineering, etc. But the practicality is on the physics side of the quantum science. So quantum chemistry, quantum physics, etc. This opens the door to all the other industries. And we have then the last takeaway of this lecture. Quantum mechanics is a relationship between matter and energy. So we could posit the energy mediums of light, magnetism, electricity, radio waves, microwaves, gamma waves, the photon, which is the wave-particle-duality of light, electrons in both the wave and particle state simultaneously. So it's all about probability and spin, quantum probability of the electron to go from energy into matter. And so that's the whole premise of the quantum mechanics, quantum physics, and its opposite would be the nuclear physics, going from a material state to a pure energy by imploding atoms and releasing the energy until those atoms reassemble, releasing the neutrinos and the radiation, etc. And so then the last part is that we have atoms, and then two or more atoms is the molecular state, but they are vibrating a non-physical quantum frequency. So what you have in information, light, etc., magnetism, their distinct information and frequency patterns can then incur the entanglement to convert that frequency of energy into the frequency of a particle or matter. So it's all about the resonant frequency. And then, of course, this then is practically applied and learned through quantum physics and quantum chemistry, because that would be an exercise in quantum mathematics. This then leads into quantum biology and quantum astronomy. I mean, you could go into any subject with both the classical and the quantum mechanics side as the function of research and development. So thank you for watching this video, and have a great day.